Welcome to Unit 1.1. It's called Rational Numbers. In this unit, we are going to be looking at the standard Explain the Properties of Rational Numbers. This will be a two-part lesson, and our lesson goal for today is for us to be able to classify numbers. That way we can understand what a rational number even is. To begin this lesson, we are going to actually ask the question, what are numbers? What are they? Well, in order for us to know what they are, we are going to give some examples of numbers. So, some examples of numbers, we could say, well, we have, let's go with 1. That's a number. We could have 2. That's also a number. We could have 3. We could have 4. We could have 5, 6. This can go on for a while. 7, 8, 9, 10. This can go on. But is that all the numbers that we know? Well, we know that there's also other numbers. We also know that we could put like a -7 in there. We could put -10. Those are also numbers. We have positives. We have negatives. We could even have 0. We could have nothing. We could also, some of you guys may have seen this type of number. We could have pi. Pi is technically a number. Yeah, I know that pi you might be thinking of the food pi, but that is actually a number, about 3.14, and so on. You also have another number, which is Euler's number, which is called E. And that is also a number, not a letter. You also have, in here, you could have square roots of like 2, square roots of 7. Those are also numbers. You could have negative of the square roots. That's also a number. You also have, we have all these numbers without decimals. Don't we have numbers with decimals? So we could have like 1.25, 1.75, or 77. We could have, there's a lot of numbers out here. This makes us wonder, or makes us think that we might need a way of organizing. Hence why we're going to learn how to classify. So let's go back to the question. What are numbers? What does it mean to have a 1 or a 2 or a 3, 4, 5? Well, typically whenever you deal with numbers, we always relate it back to some sort of objects. We could have 1 apple. We could have 2 apples. We could have 3 apples, 4 apples, 5 apples. We could have several notebooks. We could have several books in general. So generally, numbers are a representation. So these are a representation probably misspelled it, but it's okay, of objects. So numbers are just representing something, representing a quantity of something else. Numbers by themselves, you could say they are meaningless because if they are not tied to anything, then they don't necessarily mean anything. So we have these examples of numbers. We know that they are representations, but let's take these numbers and try to find stuff in common. Let's try to classify them so that when we talk about a certain type of number, we know what we're talking about. So the most basic one is called the natural numbers. Okay? Natural. If you think of numbers in general, if I said count to 10, what would you think of? You start with 1, you start with 2, then you go to 3, then you go to 4, then you go to 5, and so on. So natural numbers are the numbers that are your counting numbers. So these are going on. Those 3 dots mean that they go on forever. We could have 10, we could have 20, we could have 30, we could have 50, we can have 70, we have 100, we can have 120, we can have 475, and so on. All of these are natural numbers. Okay, the numbers that we think of naturally. These are the counting numbers. Also, we use this symbol whenever we represent natural numbers. it's just a little shorthand, a way of us being able to express what they are a lot quicker than having to write out the whole thing of natural numbers. Whole numbers. Whole numbers are very, very similar to natural numbers. Okay, we're finding stuff in common. Whole numbers, like the natural numbers, they also have 1, 2, 3, 4, 5, and so on. 1, 2, 3, 4, 5, and so on. Whole numbers also include just one other number, which is 0. So whole numbers, if we talk about whole numbers, it starts at 0 and goes on forever, all the way to infinity and beyond. Well, if we wanted to go on from there, integers. So we have our counting numbers. We have our counting numbers plus 0. Integers, take this and add something else onto this. So we are going to have 0. We're going to have 1, 2, 3, 4, 5. And this still goes on forever. What integers do is it adds numbers on the other side. So instead of being positive, now we get our negative numbers. So now we have -1, we have -2, we have -3, -4. So if we said that we wanted integers, or if we say we are working with integers, we can have our negative values. We can have our positive values. We could have it be 0 if you really wanted it to. If we said natural numbers as answers, you can only be positive. If we said whole numbers, only be positive. Example could be if you were going to buy a certain number of items. Let's say we went to the store, we were getting ready to go to school and we needed some pencils or we needed a notebook. Can we buy a negative amount of notebooks? Well, no, that kind of is ridiculous to even think about. We cannot buy a negative amount. So in that situation, we are working strictly in either natural numbers or whole numbers because we could buy 0 of them, or we could buy 1, 2, 3, 4, or 5, or even more than that if we really needed to. So we also, whenever we are thinking about these, we sometimes want to make connections to real life to see how they can actually be applied. Rational numbers. The word rational makes me think of the word ratio. Right? The first part of rational is a ratio. A ratio is a fraction. Right? So a rational number has to do with a ratio or a fraction of other numbers. In fact, this can be a ratio of integers. So a rational number is made up of a ratio, a fraction of 2 integers, as long as the bottom integer is not 0. If the bottom integer is 0, that's a division by 0. Can we divide by 0? No. If we try to divide by 0, we end up with an error. We end up with an unknown. We have no idea what that actually equals. And later on, I can go through why we know it's a unknown or undefined, but that's not for this lesson. So rational numbers are fractions. So let's write this out. Fractions. Made up or made by 2 integers. And I'm going to use our fancy little z to indicate integers because that's a lot quicker to write than having to write out the whole word integers. As long as the bottom is not 0. By the way, the bottom of the fraction is called the denominator. The top of the fraction is called the numerator. Okay? So let's just get some examples of this. Examples of a fraction. We could have 1/2. We could have -5/7. That's a fraction. We could even have 0.3 repeating on forever. Wait, I said that we had to have fractions, right? Well, 0.3 repeating on forever, that is really just 1 over 3. Decimals are included in this set as well. So our ratios can include decimals as long as those decimals can be written as fractions. If those decimals can be written as fraction, we're good. If they cannot be written as a fraction, not good. We cannot do that. Okay? So if it's a rational number, it must be able to be written as a fraction, as a ratio of 2 integers, as long as the bottom's not 0. Okay? We could also have, let's say, 0.25. 0.25 is really just 1/4. It could also be negative. Okay, that works. Here's a quick rule for this. If the decimal ends, it can be written as a fraction. If the decimal repeats itself over and over and over again, it can be written as a fraction. Okay? If the decimal goes on forever and does not repeat the same pattern, then it cannot be written as a fraction. And if that is true, then we say that that is irrational, not rational. So let's give ourselves a definition for irrational. Irrational means that it cannot be written as a fraction. So an example of this, pi. Pi is irrational. It goes on forever. And the interesting thing about pi, it does not repeat itself. Sure, it has the same numbers come over and over, but it does not repeat the same patterns over and over and over again. So that cannot be written as a fraction. Also, e, the Euler number, is also another number that cannot be written as a fraction. Let me actually give you a few more examples of this. We could have square root of 2. Square root of 2 is also irrational. That does not end up to be a decimal that has repeats. It goes on forever, but does not share the same pattern. Let me give you an actual example of a decimal that does not ever repeat. We could have negative 0.275345221, and that can go on forever. Remember, the 3 dots mean that it goes on forever. 3 dots also means that it does not necessarily follow a pattern. Okay? Remember, but up here with the integers, that one does follow a pattern. Okay? It can be continued. This really just means it can be continued on in a similar fashion. Okay? So this right here is irrational. There's no, yes, there's multiple of the same number, but they do not appear in the same order. That's what an irrational number is. By the way, if we have any square root that is not a perfect square, is irrational. Okay, so we could have negative square root of 7. That's irrational. What if we have square root of 4? Is that irrational? Well, square root of 4, if you think about your square roots, remember, when we're solving square roots, or trying to simplify square roots, we are looking for a number times itself equaling to the inside. Doesn't the square root of 4 equal 2? Is 2 itself an irrational number? No. 2 is actually integer. It's actually a whole number. It's a natural number, but it is not irrational. So square root of 4 would not be irrational. Okay? We will come back to the idea in just a moment. Okay? Real numbers. All of these are real numbers. Okay? If it's a natural number, a whole number, an integer, a rational, an irrational, these are all real numbers. Okay? Those are all the numbers that can fit on our number line. So that is real numbers. By the way, let's take note of these symbols. Okay, so natural we put a N, a fancy little N. Whole number we put a W. Integers we use Z. And there is a reason behind that. Rational is Q. Irrational, they use Q. And then they put a little tick mark. They put a little prime mark there. This prime means that it is not. Okay, so if you see that with a prime, it means it's not this other. Okay, sometimes in math, you will see a C instead of a prime. That means the same thing. The C means complement, which means that it is not that other thing. Okay, so that's what that one is saying. Then if you see the R, that's saying real number. So let's just quickly go down and get a visualization of this. So we have this nifty little diagram here. Okay? We talked about the real numbers, right? We talked about our real numbers. Inside our real numbers, we have our natural numbers, the whole numbers, the integers, the rational, and the irrational. That's what we just were talking about. Let's fill in a few pieces so that we have a working example of this. Natural numbers, we said, were the counting numbers. So 1, 2, 3, 4, going on forever, right? Whole numbers, we said, was 0. We don't have to rewrite them because we already have 1, 2, 3, 4, right? 0 is the only thing that gets added on to the natural numbers. With the integers, we have our negatives. So -1, -2, -3, and so on. Okay? Whenever you get to the fractions, by the way, any of these numbers can technically be written as a fraction. 2 can be written as a fraction. All you have to do is put 1 underneath that 2. 2 over 1 is just 2. Right? 2 divided by 1 is 2. If we did a -5 over 2, right? -5 is an integer, but it's also a fraction, right? Any number can be written over 1, which means it's also a fraction. So we could have, let's say, 1 over 2. We could have positive or negative of those. We could have 7 over 5. We can have 6 over 7. We can have 0.125. We could have 0.25 repeating on forever. We could have any number of decimals. These can be basically anything. As long as they end or as long as they start repeating themselves over and over again, those can technically be written as a fraction. Remember, irrational numbers are things like pi. These are things like e, like square root of 5, square root of 10, the positives or the negatives of any of these, right? They're either positive or negative. It could be things like 0.12579 repeating on, going on forever. Those are irrational. Okay? So that's just recapping what we just talked about. Okay? That's just a quick recap. So now let's put this into action. Example. Let's answer the following questions about these sets. Because these are sets. Each of these is self-contained, and that is basically what a set is. We have the set of natural numbers, the set of whole numbers. It self-contains these elements. Are all the natural numbers also considered to be irrational? Explain. Well, let's remember where our natural numbers are. Natural numbers are here, right? They are right here. Irrational numbers are out here. Do they share anything in common? No. They don't. So is it fair for us to be able to say that all natural numbers are also considered irrational? No, that's not a fair thing to say. So this right here, are all natural numbers also considered irrational? No. Well, why? Let's pick an example. We know 5 is natural, right? We know 5 is natural. Is 5 irrational? No. So we can say, but 5 is not, and let's just use a symbol. We're going to use a Q, fancy Q, with a little prime beside. Not irrational. Good? Okay, so that is the first example. Making sure that we understand, is it a subset? Is it included inside of this other? Here's our second one. Is every irrational number also considered to be a real number? Well, let's go back to our picture. Is every irrational number also considered to be a real number? This is our set of irrational numbers. Let me just highlight that for us right here. This is our set of irrational numbers. Is our irrational number set inside of the real number set? Yes, it is. So we know that all irrational numbers are also considered to be real numbers. Okay? So we can say, yes. I don't know why I did it lowercase, but it is. So whenever it's a yes, I'm just going to let us use the fast pass of saying it's within the circle. Okay, we're using the picture. We're using the diagram to help us out. So yes, we can say the picture has all the irrational numbers inside the real numbers. Okay? It is helpful to know what these symbols mean. Okay? And as we go along, these symbols, you're going to start getting used to the symbols. I know it might be a little bit tough right now, but as we go along, it will start making a little bit more sense. Last one for this example. By the way, this type of example is going to show up on your homework. Are all rational numbers also integers? Well, let's go back to our picture. Okay, we are looking for rational being inside of the integers. Is every rational number an integer? Well, let's look at this. Rational numbers is this big circle right here, that Q. Integers is smaller. It's inside of, right? It's inside of the bigger circle. So is every rational number also an integer? If it's not, let's find an example. An example of where it's not could be, let's say we have -1/2. This is rational. Oh, let me use the right one. We want rational, so that's a Q. So we are going to say no. -1/2 is rational, but not an integer. Right? It's rational, but it's not an integer. So we can say that no, that is not true. However, all integers are rational, but not all rational are integers. Make sure that you guys get the correct ordering of this. Okay, make sure you understand the order. Rational numbers is a bigger set. Integers is smaller and it's inside of that. Okay? So all integers are rational, but not all rational are integers. Okay, so pay attention to that little detail there. So that concludes that example. Let's go and have a few more examples. Okay? Classify simple numbers. I'm going to give us a few numbers that we're going to make up on the spot, and we are going to figure out what type of numbers these are. Okay? And we're going to try to remember our symbols. So I'm going to write them down. We have the natural numbers Remember, natural numbers are the counting numbers. We have the whole numbers, which is the natural numbers, but it includes 0. We have the integers, which is the positives, negatives, and 0. No decimals, no fractions yet. We have the rational. This is when we get our fractions, our decimals, as long as they end or repeat in some way. We have the irrationals, which are not able to be written as fractions. And we have our real numbers. Okay, those are the symbols that we can use. So, here's our number. Let's say we have number 7. Well, 7 is natural. It's a whole number. We're just classifying. It's a natural number. It's a whole number. It's a integer. It's rational. And it's real. Right? So 7 is all of these things. Okay? Let's say we have a different number. Let's say that we have negative square root of, let's go 11. Negative square root of 11 cannot be simplified. Negative square root. I said a little bit ago that square roots are always not rational, right? So this would be an irrational and naturally a real. Okay? All of these are real numbers. So whatever we classify, whatever we have here, real numbers is basically always going to be there. Okay? What if we have, let's say, negative 5 over 0? Negative 5 over 0. Is that okay? Can we have a division by 0? No, we cannot. So in other words, this right here is none of them. Okay? So this cannot be any of them. Not any of them. Okay? What if we have, let's say, 5 over 7? Well, that's not natural. That's not a whole number. That's not a integer. But this is a fraction, right? It's a fraction. So this would be rational and real. Okay? Notice if it's any of these, it's always going to have the real. We're just getting all the sets that this is part of. Every single set that this is part of. I think you guys will be able to do this part. Let me just get into the little bit more challenging section. Okay, so let's do some simplify, then classify. Let's say that we have 3 plus 5 over 8. Okay, we're going to simplify this before we can classify it. This is a certain type of number. Well, in order for us to simplify it, let's do the top first. 3 plus 5 is 8. 8 divided by 8 is 1. 1 is a natural number. It's a whole number. That's an ugly whole number symbol, but we will fix that. It's an integer. All integers are rational numbers, and it's also a real number. Okay? So if it says simplify, then classify, or if you have any number given to you, always simplify it first. Let's say we have, let's do another one. Let's say we have 5 pi plus 7 pi divided by, let's say 2 pi. We like our pi's in here. What's 5 pi plus 7 pi? Well, that's 12 pi. That's divided by 2 pi. Pi's and pi's go away. 12 divided by 2 is 6. 6 is natural. It's a whole number. It's a rational integer. It's a rational, and it's real. Okay. Another example that we could come up with, it could be, let's say we have square root of 25 divided by 7. Square root of 25 is 5. 5 over 7 is not a natural number. It's not a whole number. It's not an integer. This is rational, and it's also real. Okay? Hopefully this is making sense. Hopefully you guys are starting to get the idea of this. We want to simplify before we classify. Simplify before you classify our numbers. So let's do one more of these. And let me see. We want to do, let me find that. Okay, let's do one more of these. Let me make sure that I do. Let's do one that looks like the following. Let's say we have 8 plus 7 times 2 minus by 5 divided by, let's go 10. Well, this brings us to remember order of operations. Remember order of operations, it's PEMDAS, it's our parentheses, the exponents, so PEMDAS, PEMDAS, parentheses, exponents, multiplication or division, whichever one comes from first from left to right, and addition, subtraction, whichever one comes first from left to right. So this one, we don't have parentheses, we don't have exponents, that's fine. But we still do have a multiplication. So 7 times 2 is 14. Then we are going to go from here. 8 plus 14 gives us a 22. 22 minus by 5 is 17. And that's a fraction. Fractions are the rational and the real number.